Fine. Let's start number 38. Where is everybody? It was lunchtime at Los Alamos, sometime around 1950, and the physicist Enrico Fermi was doing what physicists do at lunch, which is argue about something enormous while eating a sandwich. The conversation had drifted to flying saucers, and then to the wider question of alien life, and the mood was casual. And then Fermi went quiet, did a little arithmetic in his head the way he always did, and asked a question that has been sitting on the chest of every astronomer since. Where is everybody? Here's what he meant. Our galaxy is old, enormously old. There have been stars burning out here for billions of years before the sun ever switched on, which means there was time. So much time for other civilizations to rise. And if even one of them had built ships and started spreading, even slow ships, even at a crawl, the math says they could have crossed the entire galaxy in a few million years. A few million years in a galaxy that's been around for 13 billion. That's the blink before the blink. So the galaxy should be full. Crowded. Loud. It should be covered in fingerprints. And it's silent. Now, we tell ourselves comforting stories about this. Maybe they're too far. Maybe we haven't listened long enough. Maybe we're not interesting. And those might all be true. But here's the thing that makes Fermi's little lunchtime question so hard to shake. The silence isn't the absence of an answer. The silence is the answer. It's data. Every empty sky, every dead frequency, every year that goes by without a single hello. That's the universe telling us something. And we don't know what. Maybe nobody's out there. Maybe something happens to everybody. Neither of those is a good option. And whichever one is true, it says something about you, sitting here, one of the only pairs of eyes the universe has ever managed to open. The quiet isn't empty. The quiet is looking back at you. Number 37. Schrodinger's cat. You know the cat. Everyone knows the cat. A cat in a box, a vial of poison, and the cat is somehow both alive and dead until you open the lid. It's become a cute little brain teaser, the kind of thing on a t-shirt. But here's what almost nobody tells you. Erwin Schrödinger did not invent that cat because he believed it. He invented it because he thought it was ridiculous. In 1935, quantum mechanics was telling physicists something genuinely disturbing. It said that a tiny particle, until you measure it, doesn't have a definite state. It exists in a smear of possibilities all at once, and only when you look does reality snap into a single answer. Schrödinger looked at that and thought, this is absurd, and I'm going to show you how absurd. So he scaled it up. He tied the fate of a big, warm, ordinary cat to one of those undecided particles. If the particle decays, the poison releases, and the cat dies. If it doesn't, the cat lives. And since the particle is in a smear of both until observed, the theory says the cat must be too. Alive and dead. A living animal held in a state that makes no sense. He meant it as a punchline. A reductio, a way of saying, look where your beautiful theory leads. Isn't that stupid? But here's the thing. Physics didn't laugh. Physics looked at the cat and said, yes, that's right. That's actually how it works. We just don't usually see it at the cat-sized scale because the fragile in-between state collapses the instant a big, messy, warm object gets tangled up in it. The satire became a lesson. The joke became a law. And Schrödinger spent his later years uneasy about the very field he'd helped build, muttering that he didn't like it and was sorry he'd ever had anything to do with it. Somewhere in a box the size of the universe, the thing you call solid reality is only ever one look away from being undecided again. The man who tried to warn us became the man who accidentally proved it. Number 36. The redshift heretic. Here is one of the load-bearing beams of modern cosmology. When we look at a distant galaxy, its light is stretched toward the red end of the spectrum, and the more it's stretched, the farther away and faster receding we say it is. Redshift equals distance. That single rule is how we measure the size of the universe, how we know it's expanding, how we build the whole map. Pull that beam out, and a lot of the ceiling comes down. Halton Arp spent his career trying to pull it out. Arp was not a crank on the fringe. He was a serious astronomer at the Great Palomar Observatory, a man who literally wrote the Atlas of Strange Galaxies that everyone else used. And while cataloging those oddballs, he kept finding things that made his skin crawl. He found quasars, objects with enormous redshifts, supposedly billions of light years away, sitting right next to nearby galaxies with small redshifts, not just near in the sky, connected, linked by visible bridges of glowing gas, as if the far object and the near object were physically tied together. But that's impossible, if redshift means distance. You can't have a bridge between two things that are billions of light years apart. Arp's conclusion was heresy. He said maybe redshift doesn't only mean distance. Maybe something else is going on. And for that, the community didn't debate him into the ground. They did something colder. They took away his telescope. His requests for observing time at Palomar were denied, again and again, until he couldn't do his work, and he eventually left the United States entirely to keep going in Germany. Here's the thing. Arp was probably wrong. Most astronomers think those alignments are coincidences of foreground and background. But that's not really the creepy part. The creepy part is how fast a field can close ranks and starve a dissenter of the one thing he needs, the sky itself. It's a small reminder that the map you trust so completely was drawn by people, and people decide who gets to keep looking. Number 35. The rare Earth hypothesis. For a long time, the fashionable, humble position has been that Earth is nothing special. Average star, average galaxy, nothing to see here. Surely the universe is full of places just like it. In the year 2000, a paleontologist and an astronomer, Peter Ward and Donald Brownlee, wrote a book that took that comfortable idea and quietly dismantled it, piece by piece. Their argument wasn't that simple, life is rare. Microbes might be everywhere. Bacteria are tough and turn up in the nastiest corners of our own planet. Their argument was that complex life, animals, things that move and think, might need an almost absurd stack of lucky conditions all at once. You might need to be in the calm suburbs of a galaxy, away from the deadly radiation of the crowded core. You might need a big planet like Jupiter parked in just the right spot to vacuum up comets that would otherwise smash you. You might need a freakishly large moon to stabilize your tilt so the seasons don't lurch. You might need plate tectonics, a molten core, a magnetic shield, liquid water, and billions of years of nothing catastrophic enough to reset the whole experiment. Stack all those odds together, and the number of planets where complex life could actually get going and stay going starts to look very, very small. Maybe we really are functionally alone, at least as far as anyone we could ever talk to. And here's the thing. This is the answer that quietly resolves Fermi's silence. And it's not a relief. Because it means one of two things about you. Either you're a fluke, a bag of chemistry that only exists because 1,000 dice all came up the same way once. Or you're something closer to a miracle, precious precisely because the universe almost never manages it. There's no comfortable version. You are either an accident, so unlikely it barely happened, or the rarest thing there is. Sit with that the next time the sky looks empty. Number 34. Particles have free will. In 2006, two mathematicians at Princeton, John Conway, the same restless genius who invented the game of life, and Simon Cochin, published something they gave a deliberately provocative name. They called it the free will theorem. And it is not philosophy dressed up as math. It's a genuine theorem, a proof, built on a few basic assumptions about how the quantum world behaves. Here's roughly what it says. If human experimenters have even a little bit of genuine free choice, the freedom to decide, say, which direction to point a measuring device, a choice not fixed in advance by the history of the universe, then the particles they measure must have an equivalent kind of freedom too. The electron's response to being measured cannot be a function of anything in its past. In their words, if we have free will, so do the particles. The choice the particle makes in that instant is genuinely not determined by everything that came before. That sounds almost charming. Little electrons with little wills. But turn it over and look at the other side, because the theorem is a two-way street, and that's where it gets cold. Flip the logic. If it should turn out that particles do not have this freedom, if their behavior is fully fixed by prior conditions, after all, then neither is yours. The same proof that could grant an electron a shred of freedom can just as easily take yours away. Your sense that you just decided something freely in this moment. The theorem says that feeling is chained to the same question as a particle's spin. And here's the thing. Nobody has settled which way it goes. We don't actually know if anything in the universe, including you, ever makes a free choice, or whether the whole thing is a film that was finished long ago and we're just watching our own frames go by. Two mathematicians proved that your freedom and an electron's are the same question. They did not prove the answer is yes. Number 33. The man Einstein said was wrong. In 1922, a Russian mathematician and meteorologist named Alexander Friedman was playing with Einstein's brand new equations of general relativity, and he found something Einstein himself had missed and, frankly, hated. Friedman's math said the universe could not be sitting still. It had to be doing something, expanding or contracting, growing or shrinking, but never static. The whole cosmos on the move. Einstein was so committed to a stable, eternal universe that he had jammed an extra term into his own equations just to hold everything still. So when Friedman's paper landed, Einstein publicly responded that the young man's calculations contained an error. The great Einstein, in print, saying, "This is wrong." It wasn't wrong. Friedman had done the math correctly, and eventually Einstein was forced to write a small, stiff retraction admitting the results were, in fact, sound. The universe really could expand. Within a few years, Edwin Hubble would look through a telescope and watch it actually doing so. But here's the thing that turns this from a nice science history anecdote into something that sits heavier. Friedman never got to see any of it land. He died in 1925, at 37 years old, of typhoid fever, years before the expanding universe became the accepted picture of reality, decades before it became the foundation of everything we now believe about the cosmos. He was right about the shape of all of existence, and it did not save him one single day. The universe he correctly described just kept expanding, indifferent, while the man who first heard it breathe was already gone. Being right is not a shield. The cosmos does not reward the ones who understand it. Number 32. Life miles beneath our feet. We tend to picture life as a thin skin on the surface of the world. Forests, oceans, us, a delicate film wrapped around a dead ball of rock, all of it running, one way or another, on sunlight. Thomas Gold, a brilliant and endlessly contrarian astrophysicist, looked at that picture and said, "You've got it backwards. The film on top might be the minority. The real biosphere might be underneath, in the dark, and it might be enormous." Gold argued that miles down inside the crust of the Earth, in the hot rock between the grains, there lives a vast population of microbes that have nothing to do with the sun at all. They don't eat light. They eat chemistry, hydrogen, methane, the heat and energy of the rock itself. He called it the deep, hot biosphere, and he suggested that if you added up all that hidden underground life, it might weigh as much as, or more than, everything living on the surface. An entire shadow ecosystem, sealed in stone, that has never seen a sunrise and never needed one. For years, this sounded like the wild idea of a man who liked wild ideas. And then we started drilling, and started looking, and we kept finding them. Microbes thriving in rock kilometers down, living things in the crust beneath the seafloor, an underground so full of quiet life that scientists now talk seriously about a deep biosphere as a real thing. Here's the thing. If life doesn't need sunlight, doesn't need a surface, doesn't need any of the things we assumed were required, then the list of places life could exist just exploded. Not just Earth's basement, but the insides of Mars, the buried oceans of frozen moons, rogue worlds drifting with no star at all. Life might not be a fragile guest that needs everything to be perfect. It might be something that hides in the dark of any warm rock, patient and enormous, waiting under the feet of anyone who happens to stand on the surface and think they're alone. Number 31. The wall on what can be known. In 1927, a young Werner Heisenberg worked out something that Einstein would fight against for the rest of his life. It's called the uncertainty principle, and it's usually explained badly, so let me try to give you the version that actually keeps physicists up at night. The bad version goes, you can't measure a particle's position and its speed at the same time, because the act of measuring bumps it. That makes it sound like a technical problem, a limit of our clumsy instruments, something a better microscope could fix someday. That's not it. That's not it at all. The real version is stranger and much worse. Heisenberg's math says the particle does not have a definite position and a definite momentum at the same time. Not that we can't find them, that they aren't there to be found. Reality itself, at the smallest scale, refuses to commit. The sharper a particle's position becomes, the more its motion dissolves into a fog of possibility, and there is nothing you can ever do, no cleverness, no future technology, to see past that fog. It's not a limit on our knowledge. It's a limit built into existence. Sit with what that means. Everything you are made of, every atom in your hands, is built out of particles that do not, at bottom, have fully defined properties until the universe is forced to choose one. There is a permanent wall running through the foundation of reality, and behind that wall, the universe keeps its own secrets, forever, from everyone, including itself. And here's the thing. We are made entirely of the stuff on the far side of that wall. You are a structure built on a foundation that is fundamentally, provably blurry. The solid, certain world you feel around you is a kind of average, a rounding off of countless tiny things that never fully decided what they were. Einstein hated this so much he spent decades trying to prove there was a hidden layer of certainty underneath. He lost. The blur is real, and it goes all the way down, and it is holding you up right now. Number 30. The Nobel laureate who rejected the Big Bang. Hannes Alfvén was not a fringe figure. He won the Nobel Prize in Physics in 1970. He essentially founded an entire field, the study of how magnetic fields and electrically charged gas, plasma, behave across space. The stuff he figured out is used every day to understand the sun, the solar wind, the auroras. He was, by any measure, one of the giants, and he spent much of his life insisting that the Big Bang was wrong. Alfvén argued that cosmologists had fallen in love with a tidy mathematical story, everything born in one instant from a single point, while ignoring the messy electric reality of the actual universe. He believed that the large-scale structure of the cosmos was shaped over immense spans of time by electromagnetic forces, by plasma and currents on a scale nobody was taking seriously, not by one clean explosion at the beginning of time. He thought the mainstream had confused the elegance of their equations with the truth of the world. The mainstream, mostly, moved on without him. The evidence for the Big Bang piled up. The afterglow of it is literally soaking the sky. And today, plasma cosmology sits well outside the accepted picture. Alf Venn died a dissenter, honored for his tools and ignored for his cosmos. Here's the thing, and I want to be careful with it, because Alf Venn was very probably wrong about the Big Bang, but he was right about something bigger and more uncomfortable. He kept pointing out that a scientific consensus is a human thing. It is built by people who train together, who cite each other, who find the same ideas beautiful. That doesn't make consensus false. Usually it's earned, but it's a good, cold reminder that the confident story we tell about the origin of everything is exactly that. A story, the current best one, held by fallible minds. A Nobel laureate stood at the edge of the room his whole life, pointing at the foundation, saying, "Are you all sure?" And the honest answer to, "Are you all sure?" is never quite yes. Number 29. The message we should never have sent. On November 16th, 1974, humanity did something that can never be undone. From the giant dish at Arecibo in Puerto Rico, a team led by the astronomer Frank Drake, the founding father of the search for alien life, beamed a message out into space. It was a simple thing, a little pattern of just over 1,000 ones and zeros that, when arranged correctly, drew a crude picture. The numbers 1 through 10, the building blocks of our DNA, a stick figure of a human being, our solar system, and the dish that was sending it. A postcard, a hello, sent toward a great cluster of 300,000 stars. It was meant as a demonstration, a celebration of what our new radio telescope could do. But it was also, quite literally, us raising our hand in a dark room and saying, "We're here." And that's where a cold argument begins, one that has split some of the brightest people alive. Because we have no idea what's out there. We assume, hopefully, that anyone advanced enough to hear us would be friendly, wise, benevolent. But we don't know that. We have exactly one example of a technological civilization, us. And our own history of what happens when an advanced culture meets a weaker one is not a comforting read. Some serious scientists argue that broadcasting our location to the cosmos is one of the most reckless things our species could possibly do. That the wise move, the move any cautious creature makes in an unknown wilderness, is to stay quiet and listen first. Here's the thing. That signal is still going. It left in 1974, and it is out there right now, moving at the speed of light, an announcement of our existence that we can never call back, never mute, never take back. We don't know if anyone will ever receive it. We don't know if that would be the best day in human history or the worst. But the decision was made by a small group of people at a party for a telescope, on our behalf, forever. The door didn't get left open. Someone opened it, on purpose, and walked away. Number 28. The alien life hiding on Earth. We spend billions of dollars and decades of effort searching for alien life. We send probes to Mars. We study the plumes of icy moons. We point telescopes at distant worlds, sniffing for the chemistry of biology. And the physicist Paul Davies raised a possibility that is either brilliant or maddening, depending on your mood. What if alien life is already here, on Earth, right under the microscope, and we've simply never noticed? His idea is called the shadow biosphere. Here's the reasoning. All known life on Earth, every animal, plant, fungus, bacterium, every organism we have ever studied shares the same basic biochemistry, the same genetic code, the same handful of molecular building blocks, all clearly descended from one common ancestor. We assume this means life started once, here, and everything is family. But Davies asked a sharper question. What if life started more than once? What if there was a second genesis, a completely independent origin of life, with different biochemistry, different building blocks, a whole separate tree, still living among us? And here's the killer part, the part that makes it genuinely creepy. Every test we have for detecting life is built to find our kind of life. Our tools look for our chemistry, our molecules, our code. A microbe from a second genesis, using a different chemistry, might be invisible to every instrument we own. It could be in the soil, in the deep ocean, in a hot spring, in the air. And our detectors would simply slide right past it, seeing nothing, because they were never designed to see something truly other. Here's the thing. We tell ourselves the great question is whether we're alone in the universe. Davies quietly points out we haven't even proven we're alone on our own planet. The most alien thing you'll ever encounter might not be waiting on some distant world. It might be a smear on a microscope slide that we keep throwing away, because it doesn't match anything in the book. Alien contact might not require a spaceship. It might just require finally looking, for once, for something that isn't us. Number 27. The particle that moves backward through time. Everything you have ever learned tells you that nothing can go faster than light. It's the great cosmic speed limit, the rule that holds the whole structure of physics together. But in 1967, a physicist named Gerald Feinberg took the rule and read the fine print. Relativity says nothing can be accelerated up to the speed of light. It never actually says a thing can't exist on the other side of that barrier, already moving faster than light, having never crossed it. Feinberg gave those hypothetical particles a name that stuck. He called them tachyons. Now, a tachyon isn't just a fast particle. Faster than light does something monstrous to time. According to relativity, if a particle moves faster than light, then for some observers, the order of events involving it gets scrambled. Effect can come before cause. A tachyon could, in principle, carry a signal into its own past. Fire the particle, and it arrives before you sent it. The tidy one-way river of time, past, then present, then future, springs a leak. Think about what that would mean if these things are real and can be controlled. You could send a message to yesterday. You could learn the answer before the question. Cause and effect, the bedrock assumption under every decision you've ever made. The reason you believe your actions today shape your tomorrow. It would no longer be a law. It would be a suggestion. Here's the thing. We've never found a tachyon, and most physicists suspect they don't exist, precisely because the paradoxes they'd create are so violent. But nobody has ever proven they can't exist. They live in that uncomfortable gap between forbidden and undiscovered. And every so often, the equations of modern physics cough one up again. A little mathematical ghost that always travels faster than light, always drags a piece of the future into the present, and always whispers the same unsettling question. Are you so sure that time only flows one way? Because the math isn't. Number 26. Life was inevitable. There are basically two stories you can tell about how you came to exist. In the first, life is a miracle, a staggeringly improbable accident, lightning striking a warm pond just right, a one-in-a-cosmic lottery fluke that we should feel impossibly lucky about. In the second, told by a young physicist named Jeremy England around 2013, life isn't a fluke at all. Life is what matter does when you leave it running. life is almost inevitable. England's idea comes out of thermodynamics, the physics of heat, energy, and disorder. Here's the rough shape of it. When you have a bunch of atoms and you pour energy through them, say from a warm sun beating down on a chemical soup, and there's a way for that energy to escape into the surroundings, then the atoms will tend, over time, to arrange themselves into structures that are really, really good at absorbing that energy and dissipating it. And it turns out that some of the best possible structures for soaking up energy and spreading it around are exactly the kinds of complex, self-organizing, self-copying arrangements that look an awful lot like life. He called it dissipative adaptation. Matter organizing itself, not by magic, not by chance, but because the laws of physics push it that way. If England is right, then given a planet, given an energy source, given enough time, the emergence of something lifelike isn't a rare accident you should be amazed happened. It's closer to a chemical inevitability. Turn up the heat, wait, and the universe starts building things that eat, grow, and reproduce, because that's the most efficient way to burn energy. Here's the thing that this quietly does to you. In this picture, you are not a miracle. You are not the improbable prize at the end of a cosmic lottery. You are the universe, doing what it always does. A clever, temporary structure that the second law of thermodynamics threw together, because you happen to be very good at taking in energy and giving off heat. That's it. You're a machine for making disorder slightly faster. It's either the most freeing thought you'll ever have, or the loneliest. The universe wasn't trying to make you. You're just what falls out when it runs. Number 25. The universe was built for you. Take the fundamental numbers of physics, the strength of gravity, the charge of an electron, the force that binds atomic nuclei together, the amount of dark energy pushing space apart. These constants have specific values, and as far as we can tell, nothing in physics demands they be exactly what they are. They could, in principle, have been different. And here's the part that has haunted cosmologists for 50 years. If you change almost any of them, even a little, you get a dead universe. Nudge the nuclear force a hair, and stars can't cook the carbon you're made of. Change the strength of gravity slightly, and either the universe collapses on itself in an instant, or it flies apart too fast for a single galaxy to form. Adjust the amount of dark energy by an amount so small it's almost obscene, and there are no structures, no stars, no chemistry, no anyone. The universe seems to be balanced on a knife's edge, and we are standing on the edge with it. In 1973, the physicist Brandon Carter gave this observation a name and made it respectable: the anthropic principle. Now, there are exactly 3 ways to explain this, and I want you to notice that none of them lets you sleep easy. 1. It's pure coincidence, and we just happen to live in the one dial setting that works, which is a coincidence so vast it barely deserves the word. 2. There are countless other universes, a whole multiverse with every possible setting of the dials, and of course, we find ourselves in a livable one, because we couldn't exist anywhere else. Which means you are one flicker of luck in an endless ocean of dead and unimaginable worlds. Or 3, the one nobody in physics likes to say out loud: the dials are set for life on purpose. That something meant for you to be here. Here's the thing. Every one of those answers is a door into a strange and enormous room. Blind luck beyond comprehension. An infinity of parallel universes. Or intention behind the equations. Pick whichever unsettles you least. Because the fact underneath all 3 doesn't go away. The universe is fine-tuned, right down to the fine print, for the existence of the exact kind of complexity that's currently reading these words, and nobody knows why. Number 24, diseases from space. Fred Hoyle was one of the most important astronomers of the 20th century. He worked out how stars forge the elements, how the carbon and oxygen and iron in your body were cooked in the hearts of stars and scattered by their deaths. That work is so foundational, it's practically gospel now. So when Hoyle turned his enormous mind toward a new idea, people had to take it seriously, even when the idea made them deeply uncomfortable. And this one did. Hoyle, working with his colleague Chandra Wickramasinghe, argued that life did not begin on Earth. It came from space. Specifically, they claimed that comets are not dirty snowballs, but flying incubators, carrying the seeds of life, organic molecules, even microbes, and seeding worlds as they pass. And they took it one enormous, notorious step further. They suggested that this rain from space never stopped. That new genetic material, new viruses, are still falling on us from comets, and that some of the great pandemics of history, outbreaks of flu, plagues, might be triggered by material drifting down from the sky. The scientific community recoiled. The idea that the flu comes from comets was ridiculed, and it effectively pushed Hoyle, a titan, out to the margins for the rest of his career. Today, the strong version, space plagues raining down on us, is not accepted, and I want to be clear about that. It's considered wrong, but here's the thing, and it's why the idea won't fully die. The gentler cousin of Hoyle's claim has quietly become respectable. We now know that comets and asteroids really do carry complex organic molecules, the building blocks of life, amino acids, the components of DNA. We've found them in meteorites and pulled them off asteroids and comets with our own spacecraft. The stuff you're made of really was, at least in part, delivered from space. Hoyle went too far and paid for it. But he was pointing at something true and strange. You are not purely of this earth. Some of your ingredients fell from the sky, and the same sky is still, quietly, dropping them. Number 23. The handshake with the future. Quantum mechanics has a dirty little secret. Nobody fully agrees on what it means. The math works perfectly. It's the most successful theory in the history of science. But when you ask what's actually happening underneath, physicists start to sweat and argue. There are a dozen different interpretations, and in 1986, a physicist named John Cramer offered one that is, honestly, one of the eeriest. He called it the transactional interpretation. To understand it, you have to know that the fundamental equations of physics are strangely two-faced about time. For most physical laws, a solution that runs forward in time and a solution that runs backward in time are both perfectly valid. The equations don't care about the direction. Usually we just throw away the backward running solution because it seems absurd. Who cares about a wave coming from the future? Cramer said, don't throw it away. Take it seriously. In his picture, every quantum event is a kind of handshake across time. When a particle is about to do something, say an electron about to emit a bit of light, it sends out an ordinary wave forward in time, offering the event. But the future receiver, the thing that will absorb that light, sends a wave backward in time, from the future to the present, confirming it. The two waves meet, past reaching forward and future reaching back, and they form a transaction, a completed handshake. Only then does the event actually happen. The present in this reading is not decided by the past alone. It is negotiated between the past and a future that is somehow already there to answer. Here's the thing. Cramer's interpretation makes exactly the same predictions as ordinary quantum mechanics. You can't use it to send a text to yesterday, so it's not crazy, it's not fringe, it's a legitimate way to read the equations. But it asks you to accept something that curls the mind. That the future is not a blank page waiting to be written. That in some quiet, structural way, tomorrow is already reaching back to shake hands with today, confirming events before they finish happening. Every moment you experience might be only half authored by the past. The other signature is coming from up ahead. Number 22. The living planet that could turn on us. In the 1970s, a British scientist named James Lovelock, working with the biologist Lynn Margulis, proposed an idea that sounds, at first, warm and almost spiritual. He noticed that Earth has an uncanny knack for keeping itself livable. The temperature, the saltiness of the oceans, the oxygen in the air. These have all stayed inside the narrow band that life needs for billions of years, even as the sun grew hotter and the continents rearranged themselves. It's as if the planet, the whole system of rock and air and ocean and living things, behaves like a single self-regulating organism, quietly adjusting the thermostat to keep itself alive. He named it after the Greek earth goddess Gaia. Scientists hated it at first. It sounded mystical, unscientific, like the planet had a soul. Lovelock spent years being mocked for it, and it took a long time before the respectable core of the idea, that life and the planet's chemistry are locked in a feedback loop that shapes the whole environment, worked its way into mainstream Earth science, where it now quietly lives under drier names. But here's the thing, and it's the part that turns the warm idea cold. If the Earth is a self-regulating system that keeps conditions stable for life, that does not mean it keeps conditions stable for you. A thermostat that has been holding the planet in a comfortable range can also, if it's pushed, flip to a new setting and hold it there just as stubbornly, one that happens to be lethal to a civilization like ours. And late in his life, Lovelock said exactly that. He warned that we were shoving the system hard, and that Gaia might respond not by dying, but by lurching to a hotter, harsher state. One perfectly fine for the planet and for life in general, and catastrophic for us. The organism doesn't hate you. That's the unsettling part. It simply doesn't need you, and it has shrugged off passengers before. Number 21. The conscious universe. Here's a question that sounds simple and is, quietly, the hardest problem in all of science. Why does it feel like anything to be you? Your brain is a lump of matter. Electrochemical signals, cells firing, atoms bumping atoms. We can more and more explain what the brain does, but we cannot explain why all that machinery is accompanied by an inner experience. Why there's someone home. Why the color red looks like something. Why pain hurts instead of just triggering a reflex in the dark. The philosopher David Chalmers gave this the name it deserves: the hard problem of consciousness. And it is brutally hard, because nothing in physics, nowhere in our description of atoms and forces, is there any hint of why matter should ever wake up and feel. So a handful of serious philosophers and physicists have started taking seriously an old idea that sounds, at first, insane. What if consciousness isn't something the brain manufactures out of dead matter at all? What if experience is a basic feature of matter itself, as fundamental as mass or charge? Not that rocks think, or that electrons have opinions, but that some faint spark of experience is woven into the very fabric of the physical world, and brains like yours are simply the places where it gets organized, concentrated, and focused into the rich thing you're feeling right now. This idea is called panpsychism, and it is no longer just a mystic's daydream. It's argued in academic journals by careful people, precisely because the alternative, getting mind from utterly mindless stuff, seems to work no better. Here's the thing. Follow that idea and the whole universe changes character. If experience is fundamental, then the awareness looking out through your eyes right now is not a lonely candle burning in a dead cosmos. It's the same stuff that fills everything: the stars, the dust, the dark between the galaxies. You would not be a brief flicker of mind in a mindless void. You'd be the universe, folding a piece of itself into a shape complex enough to look back at the rest and wonder. When you look up at the night sky and feel something, this idea says that's not a one-way street. That's the cosmos, through you, quietly becoming aware of itself. Number 20. Burned for infinite worlds. Long before anyone had a telescope, before we had the faintest proof, a former monk named Giordano Bruno stood in Renaissance Italy and said something that was, for its time, unthinkable. He said the stars were not little lamps fixed to a crystal sphere around the earth. The stars, he said, were suns. Other suns, like ours, scattered through an infinite universe, and around them circled other worlds, countless other worlds, and on some of them, other life. He didn't calculate it. He didn't observe it. He just looked up and understood something 400 years ahead of the evidence. The problem was that this was not a safe thing to believe. It shattered the comfortable picture of a small, tidy cosmos with the earth and humanity at its sacred center. It was tangled up with other ideas the authorities of his day found intolerable. And so, Bruno was arrested, held and interrogated for years, and told to take it back. He would not fully recant. And in the year 1600, in a public square in Rome called the Campo dei Fiori, the Field of Flowers, they burned him alive. Now, historians will rightly tell you that Bruno's execution was about far more than astronomy. The charges against him were mostly about theology, not cosmology. That's true, and it matters. But here's the thing, you cannot take away from him. Bruno stared into the night with nothing but his own mind, and he saw the real shape of it. Infinite space, endless suns, worlds beyond counting. And he saw it centuries before humanity could prove a word of it. Every exoplanet we now discover, every distant sun we find with a world circling it, is a quiet vindication of a man who was turned to ash for saying it too soon. He is the patron ghost of this entire list. The first person we know of who was destroyed by a true idea about the cosmos. He looked up, he was right, and it killed him. And the worlds he imagined are still being found, one by one, long after the Field of Flowers went cold. Number 19. The dark star he erased from his own book. We think of the black hole as a modern discovery, a child of Einstein and 20th century physics. But the basic, terrifying idea is far older than that, and it has one of the strangest little histories in all of science. A great mind who conceived of the black hole, then got scared of it and quietly deleted it. In 1783, an English clergyman and natural philosopher named John Michell reasoned it out first. If gravity pulls on light, he thought, then you could imagine a star so massive, so dense, that its gravity would be strong enough to stop light from escaping entirely. Light would rise, slow, and fall back. From the outside, the star would simply be invisible. A dark star. A decade later, the towering French mathematician Pierre-Simon Laplace independently reached the same conclusion and put it in print in his great popular book on the system of the world. Objects so massive that no light could ever leave them. Black holes, in all but name, in the 1790s. And then Laplace took it out. In later editions of his book, the dark stars quietly vanished. The passage was removed. The best guess is that as the understanding of light shifted, the idea started to look shaky and absurd, and Laplace, a careful man protecting his reputation, chose to unsay it. He had the black hole in his hands, in his own printed words, and he let it go because it seemed too strange to be true. Here's the thing. It took more than a century for the idea to come crawling back, this time out of Einstein's equations, and to turn out to be one of the most real and monstrous things in the universe. There are billions of these dark stars out there. There's a giant one anchoring our own galaxy. Laplace was right, decades early, and he erased his own correct idea because reality had outrun what he was willing to believe. It's a small, humbling lesson buried in the history of science. Sometimes the truth is so strange that even the genius who first finds it can't bear to keep it on the page. Number 18. The Exiled Physicist's Hidden Order. David Bohm was one of the deepest thinkers in 20th century physics, and his life is a story of exile, political exile, and then intellectual exile for the crime of asking whether the standard story was really complete. In the early 1950s, in the paranoid heat of McCarthy-era America, Bohm was hauled before the House Un-American Activities Committee, refused to name names, and found himself effectively driven out of the country. He continued his work in Brazil, then England, and from that outsider's position, he built a version of quantum mechanics that most physicists had assumed was impossible. The mainstream said the quantum world is fundamentally random and undefined. Particles have no definite position until measured, and that's just how reality is. Get used to it. Bohm refused to accept that the story had to end there. He constructed a fully worked out theory in which particles do have definite positions all along, guided by a hidden wave, a pilot wave that fills all of space. But the price of that hidden order was steep and strange. In Bohm's universe, everything is connected. The guiding wave links every particle to every other, instantly, across any distance. There is no true separateness. Underneath the world of apparently isolated objects lies what he came to call the implicate order, a deeper level of reality where everything is enfolded together into a single, unbroken whole, and the separate things we see are just that wholeness, unfolded and flattened out into the surface we experience. Here's the thing, Bohm's theory is not fringe nonsense. It's a legitimate interpretation of quantum mechanics that makes the same predictions as the standard one, and it's enjoying a quiet revival today. And what it says about you is vertiginous. In Bohm's picture, the sense that you are a separate object, bounded by your skin, distinct from the chair and the room and the distant stars. That separateness is the illusion. It's the surface. Underneath, at the level where reality is really doing its bookkeeping, you and everything else are folded into one seamless order, connected instantly across the whole universe. The loneliness of being a single separate self might be a kind of optical trick played by the shallow end of reality. Number 17. The machine the future won't let us build. This one, I promise you, is real, published physics, and it is one of the most quietly insane ideas ever proposed by serious scientists. Around 2009, two respected theoretical physicists, Holger Beck Nielsen and Masao Ninomiya, were trying to explain a run of bad luck. The Large Hadron Collider, the giant machine near Geneva, built to hunt for a particle called the Higgs boson, had suffered a string of embarrassing delays and failures. And these two physicists floated an explanation that is difficult to say with a straight face. They suggested that the universe itself was reaching back through time to sabotage the machine. Here's the logic, and it's stranger than it sounds. In their mathematical model, the production of large numbers of Higgs particles was, for deep reasons in their theory, something the universe fundamentally disliked. Something so disfavored that it would ripple backward through time to prevent it from ever happening. Not by breaking the laws of physics, but by nudging probabilities, so that any timeline heading toward mass Higgs production would keep hitting freak accidents, funding problems, technical faults. Bad luck that wasn't luck at all, but the future editing the past to stop itself from being born. And they were serious enough that they proposed an actual experiment to test it. A card game. Draw cards and let the draw decide whether to run the most sensitive experiments. If the universe really was steering events to avoid a certain future, they argued, you'd see it show up as impossibly unlikely card draws forbidding the dangerous work. The cosmos tipping its hand. Here's the thing. The Higgs was found in 2012, so the strong version of their idea didn't pan out, and most physicists filed it under brilliant people having fun at the edge of sanity. But the idea underneath it will not fully leave you alone. It takes seriously the possibility that the future is not passive, that certain outcomes might be, in some structural way, forbidden, and that the universe could enforce those rules by reaching backward and quietly rearranging the present. It suggests that some doors are locked from the other side of time, and that maybe, sometimes, the reason a thing keeps mysteriously failing to happen is that it was never, ever going to be allowed. Number 16. Your future is already written. We treat the past as fixed, and the future as open. The past already happened. It's set in stone. The future is a fog of possibility that we walk into and shape with our choices. It feels so obvious, it's barely worth saying. But there is a serious body of physics, developed largely by the brilliant and eccentric physicist Yakir Aharonov, that quietly suggests this picture is only half right. The future might be just as fixed as the past, and it might be reaching back to steer the present. Aharonov's work is built on that same strange time symmetry lurking in the quantum equations. In ordinary physics, we describe a system by its past, where it started, what it's been doing. Aharonov proposed a formalism, called the two-state vector formalism, in which a quantum system is described by two things at once: a state moving forward in time from the past, and a state moving backward in time from the future. To fully know what a particle is doing now, in this reading, you need to know not just where it came from, but where it's going to end up. The final condition is as real and as influential as the initial one. The future is a boundary on the present, pressing in from ahead. Push this to the scale of everything, and you arrive at a genuinely unsettling thought. If the universe has a fixed final state, a definite way that all of this ends, then that ending is not just a destination we're drifting toward. It's a constraint, active right now, subtly shaping which of the possible presents actually occurs. Your life would be lived not only pushed from behind by causes, but pulled from ahead by an ending that already, in some sense, exists. Here's the thing. This isn't mysticism, and it isn't a fortune teller's line. It's a careful, respected way of reading quantum mechanics, taken seriously by working physicists. And what it whispers is that free-flowing openness you feel about tomorrow may be a comforting illusion, that the shape of your ending might already be woven into the fabric of things, quietly reaching back through every moment, nudging you toward it. You're not just walking into the future may be reaching back and walking you. Number 15. Eternal intelligence. Most stories about the end of the universe are about how everything dies, the stars burn out, the last light fades, and the cosmos settles into an endless, freezing dark, the heat death, the great running down of everything. In 1979, the physicist Freeman Dyson, one of the most original minds of his century, sat down and asked a question almost nobody had bothered to ask. In that dying universe, does thought necessarily have to end too? Could a mind, could life, could intelligence find a way to survive forever, even as the universe froze around it? His paper is a strange and beautiful piece of work. Dyson showed, with careful math, that in an open, ever-expanding universe, an intelligence didn't necessarily have to die with the stars. As the cosmos cooled and energy became scarce, a mind could survive by slowing down, thinking more and more slowly, spreading each thought across longer and longer stretches of time, hibernating for eons to conserve energy, and stretching a finite supply of power across an infinite future. In principle, he argued, a being clever enough could think an infinite number of thoughts and, in a meaningful sense, live forever, even in the cold and the dark, by dialing its own existence down to a whisper. It sounds at first almost hopeful. Immortality of a kind written right into the laws of physics. But sit with the actual picture, and it turns into one of the loneliest ideas I know. Imagine being that mind. The stars long dead. The universe empty and black and colder than you can picture. And you, a flickering pattern of thought, thinking one glacial idea over a span of time that dwarfs the entire age of the universe as it is now, then going dormant for eons to save power, then thinking again, forever, alone, in the dark. Here's the thing. Later discoveries, especially the fact that the universe's expansion is accelerating, may have slammed the door on Dyson's particular escape route. An accelerating universe eventually starves even a hibernating mind. But the idea leaves a mark. It asks what you'd actually be willing to become to never end. And it quietly suggests that forever, the thing so many of us secretly long for, might be the most desolate fate of all. Not fire, not oblivion, just a single thought, alone, stretched thin across the endless cold. Number 14. The singularity solved in the trenches. In 1915, Albert Einstein unveiled his masterpiece, general relativity, a whole new theory of gravity. Gravity as the bending of space and time. The equations were monstrously difficult, and even Einstein assumed it would take years to find exact solutions to them. It took weeks, and they came from the worst place imaginable. Karl Schwarzschild was a distinguished German astronomer, and when the First World War broke out, he, already middle-aged, volunteered and went to the front. He was serving in the artillery on the Russian front, in the mud and the cold and the shell fire, calculating trajectories for the guns, when Einstein's new theory reached him. And there, in the trenches, surrounded by the machinery of death, Schwarzschild solved Einstein's equations for the space around a massive sphere. He worked it out in the middle of a war, and mailed it back to Einstein, who was stunned and presented it on his behalf. Einstein wrote back that he had not expected the solution could be found so simply. But hidden inside Schwarzschild's clean, exact solution was a monster. The math contained a point where everything broke, where if you squeezed enough mass into a small enough space, gravity became infinite, time stopped, and the equations tore. That point is the beating heart of a black hole. Schwarzschild had, from a battlefield, written down the first real description of the thing that would become the most terrifying object in the universe. He had done it while men died around him. Here's the thing, and it's the part that stays with you. Schwarzschild never got to see what he'd found become real. He contracted a cruel autoimmune disease at the front, and in 1916, just months after mailing his solution to Einstein, he died. The equation outlived the man almost immediately. He reached into the mathematics of the cosmos from inside a war he wouldn't survive, pulled out the black hole, and then the war took him, while the thing he'd discovered went on to swallow stars and anchor galaxies and haunt physics for the next 100 years. He built the door and never walked through it. The universe kept the door. Number 13. Antimatter is just time running backward. For every kind of particle in your body, there is an opposite. An antiparticle, identical, but with the opposite charge. The electron has the positron. When a particle meets its antiparticle, they annihilate in a flash of pure energy. It's the stuff of science fiction, and it's completely real. We make antimatter in laboratories. But there's a way of understanding what antimatter actually is that is stranger than any fiction, and it was first glimpsed by a physicist most people have never heard of, whose life is one of the quiet tragedies of modern science. His name was Ernst Stueckelberg, a Swiss physicist of extraordinary depth. And in trying to understand these mirror particles, he arrived at a breathtaking reinterpretation. A positron, an anti-electron moving forward in time, is mathematically identical to an ordinary electron moving backward in time. Let that land. Antimatter, in this picture, isn't a separate kind of exotic stuff. It's ordinary matter, running the wrong way down the river of time. When two particles annihilate, you can read it as one single particle coming in from the past, hitting an event, and turning around to travel back into the past again. There may be far fewer particles in the universe than we think. Just the same ones, weaving forward and backward through time, showing us different faces. It's a profound, foundational insight, and it sits at the root of how we understand particle physics today. But here's the thing. Stueckelberg was ahead of his time and out of the spotlight, working in relative isolation, and again his deepest ideas were arrived at independently by more famous men who got the credit, the fame, and the Nobel Prizes. He watched it happen. He struggled with his mental health, spent time institutionalized, and in his later years reportedly walked the halls of the university with his dog, a brilliant, broken man whose name most physicists barely know. The person who first saw that antimatter might be time running backward was himself, in a way, erased, running against the current of recognition while others floated forward on his ideas. Number 12. The student Eddington humiliated. In 1930, a 19-year-old from India named Subramanian Chandrasekhar was on a long boat journey to England to study physics. And to pass the time on the voyage, he did a calculation that would eventually rewrite our understanding of how stars die. He was thinking about white dwarfs, the dense, burnt-out cores that stars like our sun leave behind. The assumption was that every star ends this way, settling into a stable little cinder. But Chandrasekhar, folding Einstein's relativity into the physics of these dying stars, found a limit. If a star's leftover core was heavier than about 1.5 times the mass of our sun, it could not settle down. Nothing could hold it up. It would have to keep collapsing, crushing itself, past the white dwarf, into something unknown and monstrous. He had, at 19, found the doorway to the black hole, and a few years later, in 1935, at a meeting of the Royal Astronomical Society in London, he stood up to present it. In the audience sat Sir Arthur Eddington, the most famous, most powerful astronomer in the world, a titan, and a man who had been almost a mentor to the young Chandra. Eddington rose after the talk, and in front of the assembled community, he ridiculed it. He tore the young man's work apart, called the idea absurd, suggested there must be some law of nature to prevent a star from behaving so ridiculously. Coming from a god of the field, it was devastating. Chandra was humiliated, and the sheer weight of Eddington's authority pushed the idea into the shadows for decades. Here's the thing. Chandrasekhar was right. Completely, exactly right. That limit is real. It bears his name to this day. The Chandrasekhar limit. And it's fundamental to how we understand the death of stars and the birth of black holes. He eventually won the Nobel Prize for it, nearly 50 years later. But think about what that public humiliation cost. Not just one young man's pride, but decades of progress, frozen because a powerful old man couldn't stomach a truth a teenager had found. The black hole was sitting right there, discovered in 1935, and human ego, not physics, is part of why it took the world so long to admit it was real. Number 11. The one-electron universe. One night in 1940, the great physicist John Wheeler picked up the phone and called his student, a young man named Richard Feynman, and said something so strange that Feynman remembered it for the rest of his life. Wheeler said, "Feynman, I know why all electrons have the same charge and the same mass." And Feynman said, "Why?" And Wheeler said, "Because they are all the same electron." Here's what he meant, and it grows directly out of that idea we just met, that a particle moving backward in time looks like its antiparticle. Wheeler imagined a single electron, one lonely particle, weaving forward and backward through time in an unimaginably complicated tangle. Every time it moves forward through the present moment, it shows up as one of the electrons in your body, in this room, in a distant star. Every time it doubles back and moves backward through the present, it appears as a positron, an antimatter twin, a single thread stitching back and forth through all of time, and at any given instant that one thread crosses through now, trillions upon trillions of times. And every crossing is a particle. Every electron in the universe, in this picture, is the same object, seen over and over at different points along its one endless, looping journey. It explains something real and puzzling. Why every electron is perfectly, exactly identical, indistinguishable down to the last decimal. Of course they're identical. They're the same one. Here's the thing. There's a problem with the idea, and Feynman spotted it immediately. There'd have to be as much antimatter as matter, and there isn't. So the strict version doesn't work as a literal theory of our universe. But it was never really the point. The point is what it does to your sense of yourself. Every electron in your hand, every electron in your brain, firing off the thought you're having right now, might be the same single particle as every electron in the farthest galaxy. One entity, threaded through all of space and all of time, briefly wearing the mask of you. You are not made of countless separate specks. You might be made of one thing, seen from countless angles, and so is everything else. The loneliness of being a separate self and the crowd of the entire cosmos might be, at the bottom, the same single lonely particle. Number 10. The universe made in a lab. Our best theory of the birth of the cosmos is called inflation. It says that in the first unimaginably tiny fraction of a second, the infant universe underwent a burst of staggering expansion, blowing up from smaller than an atom to something enormous in less time than it takes to say it. The physicist André Linde is one of the chief architects of this theory, and Linde, following his own equations to their strange conclusion, arrived at a possibility that he has discussed, half smiling, for decades, because it's difficult to know whether to laugh or to feel very small. According to the physics of inflation, it might be possible to create a universe, in a laboratory, on purpose. The idea runs like this. Because inflation takes a microscopic seed and blows it up into an entire cosmos, you don't need much to start one. In principle, Linde argued, a sufficiently advanced physicist could take a tiny amount of matter in exactly the right hyperdense state and trigger inflation, creating a new baby universe. It wouldn't blow up your lab. It would balloon outward into its own separate space, pinching off from ours through a microscopic bridge and then sealing away, a whole new cosmos budding off into its own existence, invisible to its creator forever after. A universe cooked up by a being with the right technology and a bad enough idea. And here is where it turns the mirror on you. Because if a physicist in our universe could, in principle, create a new universe, then what exactly is our universe? Linde has openly wondered this. Maybe ours was made. Maybe the Big Bang was not a mindless accident, but an experiment, some entity in a higher cosmos, running the equivalent of a lab procedure, sparking off the space you're sitting in as one of countless budded-off worlds. Maybe there's a signature buried in the laws of physics, a message left by the maker. Maybe the fine-tuning we talked about earlier isn't luck or multiverse at all. Maybe somebody set the dials. Here's the thing. This isn't a religion, and it isn't a stoner's midnight thought. It's a serious idea from one of the founders of modern cosmology, following his own respected physics off the edge of the map, and it leaves you with a question you can't quite put down. If making a universe is just advanced physics, then the creator of everything you've ever known might not be a god at all. It might just be somebody, somewhere, in a lab, who ran the experiment. Number 9. Consciousness woven into space-time. We come back to the hardest problem, why you are conscious at all, but now with one of the boldest, most controversial answers anyone has ever dared to propose. It comes from Roger Penrose, a mathematical physicist so eminent he shared a Nobel Prize for his work on black holes, teaming up with an anesthesiologist named Stuart Hameroff. And their idea is either one of the deepest insights of our age, or a beautiful mistake, and honestly, nobody yet knows which. Penrose started from a strange conviction that human understanding cannot be fully captured by any computer, any set of fixed rules. There is something about genuine insight, he argued, that goes beyond mere calculation. And if the brain is doing something no computer can do, then the brain must be tapping into some physics deeper than ordinary electrical signals between cells. He suspected the answer lay in quantum mechanics, and specifically in the mysterious moment when the fuzzy quantum world of possibilities collapses into one definite reality. Penrose believed that collapse is tied to gravity, to the very geometry of space-time itself. And with Hameroff, he proposed that inside your neurons, in tiny structures called microtubules, exactly these gravitational quantum collapses are happening, and that each one is a flicker of conscious experience. In their theory, your mind is not just chemistry. It is a series of tiny events where the quantum structure of space-time itself folds and chooses, over and over, inside your head. If they're right, consciousness is not something the brain secretes like a gland. It's a bridge, a place where your mind reaches down and touches the fundamental fabric of reality, the same space-time that bends around black holes and carries the light of galaxies. Your every thought would be, quite literally, woven into the geometry of the cosmos. Here's the thing. Most physicists and most neuroscientists think they're wrong. The brain is warm and wet and chaotic, and quantum effects are supposed to fall apart almost instantly in that environment. The objection has been thrown at Penrose for 30 years, and experiments keep trying to rule the idea out. And yet, he has never backed down, and recent hints that quantum effects might survive in biology longer than anyone believed keep the door from fully closing. Whether or not the specifics hold, the ambition of the idea is staggering. It says the thing you are, your awareness, your inner light, might not be a lonely accident sealed inside your skull. It might be the universe's own deepest layer, briefly folding itself into a shape that can wonder what it is. Number 8. The omega point. Frank Tipler was a respected mathematical physicist, a serious relativist who understood Einstein's equations as well as almost anyone. And then he used that expertise to make a claim so audacious that most of his colleagues quietly decided he had wandered off the edge of the world. He argued, using physics, that the universe will end by resurrecting every being who has ever lived. That something functionally identical to heaven is not a matter of faith, but of cosmology. Here's the shape of the argument, and you have to admire the nerve of it. Tipler imagined a universe that eventually stops expanding and begins to collapse back in on itself, hurtling toward a final crunch at the end of time, a single point he called the omega point. As the universe collapsed, he argued, the chaotic energy of that collapse could be harnessed by whatever intelligence still existed to perform computation. And not just a little computation. As the collapse funneled toward that final instant, the rate of processing would climb toward infinity. An infinite amount of computation packed into the last moment of time. And with infinite computing power, Tipler said, that final intelligence could simulate everything, every possible mind, every person who had ever lived, reconstructed perfectly, down to the last memory, resurrected inside an infinite computation, to live again forever in the last instant of the universe, which, from the inside, would feel like eternity. Heaven at the end of physics. Everyone you've lost, everyone who ever was, brought back, not by God, but by the machinery of a dying cosmos, computing itself into paradise. Here's the thing. Tipler's colleagues largely regarded this as brilliant math bent into the service of wishful thinking, and worse, the specific cosmology it needs, a collapsing universe, appears to be wrong. We now know the universe's expansion is accelerating, not slowing toward a crunch, which knocks the legs out from under the omega point as he described it. And yet, he never took it back. He staked his reputation on the idea that the end of time is not death, but a reckoning, a great return, and he defended it to the end. A serious scientist, utterly alone, with a theory that promised to give everyone their dead back. The creepy part isn't that he was probably wrong. It's how badly a part of all of us wants him to have been right. Number 7. The time machine made of cosmic strings. Time travel into the past is supposed to be impossible. The stuff of movies. Forbidden by common sense. A paradox factory. But here's the uncomfortable truth that physicists live with quietly. Einstein's general relativity, our best and most tested theory of space and time, does not actually forbid it. The equations allow, under extreme enough conditions, for loops in time. Paths through spacetime that curve back and reconnect with their own past. And in 1991, the astrophysicist J. Richard Gott found a specific, disturbingly concrete way to build one. His ingredient was something called a cosmic string. These are hypothetical objects, incredibly thin, incredibly dense threads of pure energy, thinner than an atom but stretching across the cosmos, that may have been left over from the birth of the universe, frozen in cracks in the fabric of space. A cosmic string is so dense that it warps the space around it, not by curving it into a bowl, but by snipping a wedge out of it, so that the geometry near the string is subtly, strangely folded. And Gott showed, with rigorous mathematics, that if you took two of these cosmic strings and sent them flying past each other at enormous speed, the combined warping of space would bend the paths through spacetime so severely that a loop would open. A route you could travel along that would bring you back to your own past. A time machine, assembled from the leftover threads of creation, running entirely on accepted mainstream physics. Here's the thing. Nobody knows for certain whether cosmic strings exist, and building this contraption would require engineering on a scale beyond anything imaginable. So you're safe. Nobody's rewriting your yesterday. But that is not what should keep you up at night. What should keep you up is that the door isn't locked. Our deepest, most successful theory of reality, the one that predicts black holes and gravitational waves and gets everything right, permits travel into the past. The impossibility of changing what already happened, the one-way flow of time you have staked your entire life on, is not guaranteed by the laws of physics. It's just very, very hard to violate. The past might not be closed and finished and safe. It might just be waiting for the right two threads to cross. Number 6. The dark side of the warp drive. In 1994, a young Mexican physicist named Miguel Alcubierre did something wonderful. He was a fan of Star Trek, and he wondered whether the warp drive, faster than light travel, could be made to work in real physics, inside Einstein's equations. And astonishingly, he found a way. You can't accelerate through the speed of light. That's forbidden. But Alcubierre realized you could cheat. You don't move the ship through space at all. Instead, you warp space itself. You contract space in front of the ship and expand it behind, creating a bubble, a wave of distorted spacetime, and you surf it. The ship sits still inside its bubble, moving no faster than light locally, while the bubble itself carries it across the galaxy faster than light could ever travel. It's beautiful. It's real relativity. It turned science fiction into a legitimate line on a physicist's whiteboard. The world got excited. NASA looked into it. It felt like the future had cracked open. But then physicists started studying Alcubierre's bubble more carefully, and they found something lurking inside the dream. A horror hidden in the machinery. To hold the warp bubble open, you'd need a form of exotic matter with negative energy, something we're not sure even exists in the amounts required. That was the first problem. But the second one is the one that gives me chills. As the warp bubble travels, it sweeps up particles, stray bits of matter and radiation from space, gathered along the front edge of the bubble like a cosmic snowplow. And all that captured energy piles up, compressed against the leading wall of the bubble, held there through the whole journey. When the ship arrives and the bubble switches off, all of it releases at once, an unimaginable blast of high-energy radiation, fired forward in the direction of travel. Here's the thing. You'd cross the galaxy in a warp bubble to reach some peaceful destination, and arrive carrying a bow wave of built-up energy so violent it could annihilate whatever was waiting there. The very act of arriving would be an act of destruction, an accidental weapon that sterilizes your destination the instant you drop out of warp. The most beautiful idea in the physics of space travel, the one that promised to unite us with the stars, turns out to have a blade built into its front edge. Sometimes the dream and the nightmare are the same equation. It just depends which term you read last. Number 5. The particle he was ashamed to invent. In 1930, physics had a crisis. In a certain kind of radioactive decay, energy seemed to be vanishing. You'd measure everything before, measure everything after, and some energy was simply gone. And the law of conservation of energy, one of the most sacred principles in all of science, appeared to be broken. Some of the greatest minds of the age were ready to consider throwing the law out. And then Wolfgang Pauli, one of the most brilliant and famously savage critics in physics, proposed a desperate fix. He suggested that the missing energy was being carried away by a new particle, a particle nobody had ever seen, a particle so faint, so ghostly, that it barely interacted with matter at all, one that could pass through the entire Earth without touching a thing. He proposed it in a letter, which he playfully addressed to dear radioactive ladies and gentlemen. And then, having proposed it, Pauli was horrified at himself, because he believed that a real scientist should only ever predict things that could actually be detected, tested, confirmed. And he had just invented a particle that seemed, by its very nature, impossible to ever detect. He is said to have confessed to a friend, with real anguish, "I have done a terrible thing. I have postulated a particle that cannot be detected." He thought he had committed a kind of scientific sin, patching a hole in physics with a ghost that could never be caught, an untestable phantom conjured purely to save the equations. Here's the thing. That ghost was the neutrino, and it was real. It took 26 years, but in 1956, other physicists finally, definitively caught one. Pauli's undetectable particle was detected, and today, we know that neutrinos are among the most abundant particles in the entire universe. Right now, as you hear this, trillions of them are streaming through your body every single second, born in the heart of the sun, passing through you and the earth, and out the other side, as if you were made of empty space. The particle Pauli was ashamed to have invented turned out to be one of the most fundamental things there is. He thought he'd cheated. Instead, he'd heard, before anyone else, the whisper of a billion, trillion ghosts pouring through all of us, all the time, unfelt. Sometimes, the terrible thing you're ashamed of turns out to be the truest thing you ever said. Number 4, the universe where time loops. Kurt Gödel was, by many accounts, the greatest logician since Aristotle. A mind of almost frightening precision. He had already shaken mathematics to its foundations with his famous incompleteness theorems, which proved that in any logical system there are true statements that can never be proven. And then, in the late 1940s, this same man turned his attention to his close friend and walking companion at Princeton, Albert Einstein, and to Einstein's theory of gravity. As a gift for Einstein's 70th birthday, Gödel gave him not a card, but a new solution to his equations. And that solution contained something that reportedly disturbed Einstein deeply. Gödel found that if the entire universe were rotating, then the equations of general relativity would permit something monstrous. In such a universe, space-time would be so twisted by the rotation that you could set off in a spaceship, travel in a great loop out into space, and arrive back not just at your starting place, but at your starting time. Or earlier. You could, by flying far enough in the right direction, return to your own past. Not a metaphor. A mathematically valid consequence of Einstein's own theory. A universe in which the past is a place you can revisit. In which time is not a river, but a closed ring. And every moment, including this one, always was and always will be. Endlessly. Here's the thing. Our universe doesn't appear to be rotating the way Gödel's model required, so we're likely spared the paradoxes. But that was never what rattled Einstein and Gödel. What rattled them is that the theory allowed it at all. If the flow of time can be bent into a circle by the mere rotation of the cosmos, then time is not the fundamental, forward-marching thing we feel it to be. It's a feature of a particular arrangement of matter, and it could, in principle, be otherwise. Gödel took this seriously enough that he came to believe time itself, the passage you feel, so certainly, might be an illusion. And here is the darkness that closes around this one. That same magnificent, precise mind, the man who proved the limits of logic and bent time into a loop, was consumed, in the end, by paranoia. Gödel became convinced that someone was trying to poison his food, and he would only eat meals prepared by his wife. When she was hospitalized and could no longer cook for him, he simply stopped eating. He starved himself to death in 1978, weighing 65 pounds, killed by the logic of his own fear. The greatest logician of the age, who could hold the structure of infinity and the shape of time in his head, could not save himself from the loop his own mind had closed around him. Number 3. The physicist who vanished. Enrico Fermi, the same Fermi who asked, "Where is everybody?" did not hand out praise lightly. He once ranked the physicists he'd known, and he said that there are several categories of genius, first-rate scientists who make great discoveries. But then, he said, there are geniuses like Galileo and Newton. And Ettore Majorana, Fermi said, was one of those. In the same breath as Galileo and Newton. That is who we're talking about. And that is who vanished. Majorana was a young Italian physicist of terrifying brilliance and painful shyness. He would solve enormous problems in his head, scribble the answer on a cigarette packet, and then throw the packet away, not bothering to publish, indifferent to the credit. Among the ideas he did leave behind was a beautiful and profound one. He predicted the existence of a particle that is its own antiparticle, a particle with no separate mirror twin that is somehow both matter and antimatter at once. We call them Majorana fermions, and physicists are still, to this day, hunting for them, chasing them in exotic materials and quantum experiments, because they might hold the key to building a stable quantum computer. His ghost still shapes the frontier of physics. And then, in March of 1938, Ettore Majorana got on a boat. He withdrew a large sum of money, wrote some unsettling notes, boarded a ship traveling by night from Palermo to Naples across the water, and was never seen again. No body was ever found. Did he jump? Did he kill himself? Did he stage his own death and slip away to live in a monastery, or in Argentina, as some later claimed to have seen him. Was it despair, or a deliberate perfect disappearance by a man who no longer wished to be found? Nearly 90 years later, nobody knows. The case has never been closed. Here's the thing that makes this one land so strangely on a list like this. Majorana predicted a particle that is its own opposite, a thing that is somehow present and absent at the same time, matter and antimatter in one. And then he himself became exactly that, present in every physics lab still chasing his particle, and utterly, permanently absent. He dissolved out of the world as cleanly as a solution to an equation, leaving only the math behind. A man who wrote down the physics of a thing that is its own shadow, and then stepped into the dark and became one. Number 2, the day he found black holes, then built the bomb. We remember Robert Oppenheimer for one thing, the bomb. The father of the atomic bomb, standing in the desert at the first nuclear test, the words from ancient scripture rising in his mind. Now I am become death, the destroyer of worlds. That is the image seared into history. But there is another Oppenheimer, an earlier one, and the timing of what he did is so heavy with dark poetry that it barely feels real. Before the bomb, Oppenheimer was a brilliant theoretical physicist, and in the 1930s he turned his mind to what happens when a truly massive star dies. Building on the kind of collapse Chandrasekhar had glimpsed, Oppenheimer and his student Hartland Snyder worked out, in full, what happens when a giant star runs out of fuel and nothing can hold it up anymore. Their answer was staggering. The star collapses. And it doesn't stop. It collapses past the white dwarf, past the neutron star, collapsing forever, pulling itself down into a point until its gravity seals it off from the rest of the universe entirely, a region from which not even light can escape. They had written down, for the first time in complete and rigorous detail, the formation of a black hole, the most complete early description of the darkest object in existence. And here's the detail that stops the breath. Their paper was published on September 1st, 1939, the exact same day that Germany invaded Poland, the day the Second World War began. On the very morning that the world plunged into the darkness that would consume tens of millions of lives, Robert Oppenheimer's description of literal darkness, of stars collapsing into inescapable black pits, appeared in print. And then Oppenheimer set the black hole down. He walked away from the pure, beautiful physics of the collapsing star, and he gave the next years of his life to building the weapon that would haunt him until his dying day, a weapon whose fireball was, in its way, the opposite of his black hole, not a thing that swallows all light, but a thing that unleashes a false and terrible sun. Here's the thing. One man, in one life, reached to the two absolute poles of what matter can do. He described the black hole, where light and everything else falls in and never comes out. And then he built the bomb, where matter itself is torn open to release the light and fire of a star. Creation and annihilation, the deepest dark and the most violent light, discovered and unleashed by the same pair of hands, beginning on the day the world caught fire. Some lives are just heavier than others. His may be the heaviest a scientist has ever carried. Number 1. Many worlds. In 1957, a young graduate student at Princeton named Hugh Everett III proposed a solution to the deepest puzzle in quantum mechanics, and it is either the most extravagant idea in the history of science or simply the truth. And the most unsettling part is that plenty of brilliant people now think it's the truth. Remember the problem. A quantum particle exists in a smear of possibilities, and only when we measure it does it snap into one definite outcome. Everett looked at that snap, the collapse, the moment the many become one, and asked a devastating question. What if it never happens? What if the collapse is a fiction, and all the possibilities are equally real? Here is what that means. Every time a quantum event occurs with more than one possible outcome, and that is constantly, everywhere, in every atom of your body and the air around you, the universe does not choose. It splits. It branches into separate, parallel realities, one for each outcome, all of them real, all of them just as solid as the one you feel yourself in. In one branch, the particle went left. In another, right. In one branch, you got the good news. In another, the bad. And this happens ceaselessly, dividing the world into an ever-growing, unimaginable tree of parallel universes, each containing a version of you, splitting off, living on, never able to touch or see the others. There are, right now, countless copies of you, in countless worlds, branching away from this exact moment, each of them certain that theirs is the only one. Everett called it the relative state formulation. The world came to call it the many worlds interpretation. And when he presented it, physics rejected it. Coldly, the great Niels Bohr's circle dismissed it. Everett, wounded and disillusioned, walked away from theoretical physics entirely. He went to work for the defense establishment, doing calculations about nuclear war. How many millions would die in which scenarios? He grew heavy, drank hard, chain-smoked, and became remote. He was so estranged from the world that when he died of a heart attack in 1982, at just 51, he had asked that his ashes be thrown out with the trash, and his family honored it. But the story doesn't end with his death, and this is the part that I cannot get out of my head. Everett had a daughter, Elizabeth. She struggled for years, and sometime after her father's death, she took her own life. And in her suicide note, she wrote that she was going to a parallel universe, to be with her father. She used his theory, the one the world had rejected, the one that had broken him, as the map for where she was going. She believed, or needed to believe, that in one of the infinite branches, they would be together. And here's the thing. Here, at the end of all of this, is where every one of these theories has been quietly pointing. Because the deepest and strangest ideas we've ever had about the cosmos, the many worlds, the loops in time, the conscious universe, the particle that is its own shadow, the mind stretched across the dark, every one of them, in the end, is not really about space at all. It's about you. What you are, whether you're one thing or many, whether you chose anything or nothing, whether you're a fluke or a miracle or a branch on an infinite tree, whether the person you are is the only one, or the loneliest of an uncountable crowd. Everett looked into the equations and saw a universe endlessly splitting into copies of us, and it cost him everything, and his daughter followed the map he drew straight out of this world. We don't know if he was right. That may be the most haunting thing of all, that the answer to whether there are infinite versions of you living out every life you didn't is not fantasy and not settled, but a live and serious question in physics right now. And you will almost certainly leave this life without ever knowing. Just one version of you, wondering about all the others. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.